So what really happens inside a power diode when it switches off? Let's dive in. You'd think that gate just slams shut instantly, right? Well, in the real world, it's not that simple. See, an ideal diode is a perfect switch, but a real one, it's got delays and other weird behaviors. And the key to all of this is something called DIDT. It's just how fast the current changes. So as the diode turns off, the current doesn't just stop. Nope, it ramps down at that DIDT rate. But here's the crazy part. The current actually overshoots and goes negative for a little bit. Wild, right? That's called reverse recovery. Think of it as a leftover charge that needs to get swept out of the way. So why should you care about this little backward current? What's the big deal? Well, a higher DIDT means a faster drop, and that can cause some serious problems. We're talking damage. And that peak reverse current, which we call IRM, is directly linked to DIDT. Higher DIDT means higher IRM. And the math backs this up. Look, as DIDT goes up, so does that pesky reverse current spike. We also measure how long this whole negative current thing lasts. That's the reverse recovery time, or TRR. Now here's the twist. A higher DCDT actually makes this recovery time shorter. It's a trade-off. So if you've got, say, 30 amps per microsecond, you're looking at a short but very intense spike. So to put it simply, the faster you try to switch it off, the bigger the kickback you get. And that kickback isn't just current. It can create a huge, damaging voltage spike across the diode. Ouch. Okay, so how do engineers actually deal with this problem? Well, there are a couple of main tricks. First up, you pick the right diode. A soft recovery one turns off much more gently than an abrupt one. The other trick is adding a snubber circuit. It's basically a shock absorber for that nasty voltage spike. Which brings us to a huge question in electronics. Is faster always better? As we just saw, not always.
Dhanyavada. Subscribe for appreciation.